Imagine you walk outside on a clear night, expecting to see the moon. You know what it should look like from memory: a bright white disk or a glowing crescent hanging above rooftops and trees. You know roughly where it should be in the sky for that phase of the month. Your brain carries a quiet expectation. If the sky is clear, the moon will be there. But tonight, in this thought experiment, you look up and the sky feels wrong. There are stars, yes. The familiar constellations are still there. Planets shine as steady points of light. But the moon is missing. There is a hole in your expectations, a dark gap where your mind insists something bright should be. For a moment, it feels like a small, personal disturbance, something you or your memory has failed to do properly. Then you open your phone, and you see that people all around the world are asking the same question in 100 languages. Where is the moon? In this story, we are not going to make the moon truly vanish. Instead, we are going to do something more interesting. We will ask a different kind of question. How deeply does the moon already control life on Earth, in ways you may never have noticed? Welcome to Scientists Also Sleep. For the next few parts, we will treat the moon not just as a pretty object in the sky, but as a piece of planetary machinery. We will see how its gravity sculpts the oceans, how its slow pull steadies Earth's spin, how its phases whisper to the clocks inside living bodies, and how human cultures have built calendars, myths, and science around its changing face. To begin, we need a clear picture of what the moon actually is. It is easy to think of the moon as a small lamp above Earth, but physically, it is a world in its own right. The moon is about 1/4 of Earth's diameter. If you lined up 4 moons side by side, you would span the width of Earth. In terms of mass, however, it is much smaller, only about 1/81st of Earth's mass. It orbits our planet at an average distance of about 384,000 kilometers. If you could drive to the moon on a highway, and if you never stopped and always drove at 100 kilometers per hour, the trip would take you more than 5 months. The moon always shows the same face to Earth. This is called tidal locking. The time it takes to spin once on its axis is the same as the time it takes to orbit once around Earth. From our point of view, the moon seems to hover like a slowly changing disk, waxing and waning as the geometry between sun, Earth, and moon shifts. On the far side, there are craters and highlands that no human eye on the ground has ever seen directly. The moon is not bright by itself. It shines by reflecting sunlight. Its pale glow is sunlight scattered off gray rock and dust. When you see the full moon, you are seeing a world made of ancient lava plains and crater rims acting as a giant, natural mirror. So how does this cold, airless sphere control life on a blue, living world far below? The first and most powerful channel is gravity. Every bit of mass in the universe attracts every other bit. Earth pulls on the moon and the moon pulls on Earth. It is that mutual pull that keeps the moon in its orbit. But gravity does not act as a single, uniform force. It is a little stronger on the side of Earth that is closer to the moon, and a little weaker on the side that is farther away. That difference is what creates tides. To picture this, imagine Earth covered in a shell of water. The moon's gravity pulls a bulge of water toward it on the near side. On the far side, water is pulled a little less strongly than the solid Earth under it, so the planet effectively moves slightly away from that water, creating a second bulge there. The result is two tidal bulges on opposite sides of Earth. As Earth rotates once every 24 hours under these bulges, any given coastline passes through regions of higher and lower water level. To an observer on the shore, this appears as high tide and low tide. In reality, the pattern is more complicated. The sun also contributes its own tides. The shape of ocean basins, the depth of the water, the presence of islands and coastlines, and Earth's rotation all twist and reshape the idealized tidal bulges into complex patterns of currents and sea level changes. Some places see two high tides per day of roughly equal height. Others experience one dominant high tide and one much weaker one. In a few locations, tides are very small. But everywhere there is open ocean, the moon is working quietly, every hour of every day, lifting and lowering billions of tons of water. You might think of tides as an inconvenience for beachgoers and boat owners, or as a picturesque background to coastal life. In reality, they are one of the major engines that move water, nutrients, and energy around the planet. When the tide comes in, it floods coastal flats, salt marshes, and mangrove forests. When it goes out, it exposes rocks, sand, and mud to the air. Twice a day in many places, vast areas of the coastline move rhythmically between underwater and exposed states. That constant pulsing is not just scenery. It creates entire worlds of opportunity for life. The intertidal zone, the region between high and low tide marks, is one of the harshest and richest habitats on Earth. Organisms that live there must endure both immersion in seawater and exposure to air. They must withstand waves, drying winds, changes in temperature, and the risk of being eaten by predators from both sea and land. Yet, for those that can handle these challenges, the rewards are huge. Abundant nutrients, sunlight when the sun is present, and constant delivery of fresh water and food with the tides. Barnacles cement themselves to rocks and endure pounding waves. Mussels and oysters anchor in clusters, filtering plankton from water during high tide and closing tightly during low tide to avoid drying out. Crabs scuttle in and out with the waves, feeding on whatever the water brings. Seaweeds and seagrasses flex with the currents, trapping sediment and creating safe havens for small animals. Without the moon, these tidal worlds would be very different. The sun does raise tides, but they are weaker. The combined pattern of lunar and solar tides creates spring tides, when the two work together, and neap tides, when they oppose each other and produce smaller variations. If the moon were gone, only the weaker solar tides would remain. Many intertidal zones would shrink or vanish. Coastal ecosystems would reorganize completely. Tides also help mix the oceans. When water moves up and down along continental shelves and through narrow straits, it creates turbulent flows that stir warm surface waters and cold deep waters together. This mixing moves heat and nutrients through the ocean. Some estimates suggest that tidal mixing contributes a significant fraction of the energy that drives large-scale ocean circulation. Ocean circulation, in turn, helps regulate climate by moving heat between the equator and the poles. The details are complex and still an active area of research, but the basic idea is clear. The moon's pull helps keep the ocean's massive engine turning. And oceans are not just water. They are home to most of Earth's living biomass and a major part of its climate machinery. So when you see tides, you are seeing one of the main ways the moon controls life, by physically moving the medium that life in the sea depends on. The moon's influence is not limited to water level. Its regular orbit and changing phases create patterns of light and time that many organisms can detect and use. The moon waxes from thin crescent to full, and then wanes back again over about 29.5 days. That cycle creates a roughly monthly rhythm of moonlight, combined with the daily rhythm of rising and setting with Earth's rotation, and the slower cycle of changing angle in the sky over the year. It forms a complex but highly regular pattern. On a bright full moon night, landscapes that would be pitch black under a new moon are bathed in a soft, silvery light. Predators can see farther. Prey can see predators sooner. Nocturnal animals adjust their behavior. Some hunt more under the brightness. Others hide more to avoid being seen. Over millions of years, natural selection has tuned the senses and behaviors of many species to these changing light levels. Some coral species, for example, time their mass spawning events to certain combinations of water temperature, day length, and lunar phase. Grunion fish come onto sandy beaches to lay eggs in the zone reached only by the highest tides, timed to specific nights of the lunar cycle. Many species of invertebrates, fish, and even some mammals show circulunar rhythms, internal clocks with periods close to the lunar month. Humans, too, have felt the moon's presence deeply. Long before our ancestors could calculate orbital mechanics, they watched the moon carefully. They used its phases to mark time. They wove its changing face into myths about gods, animals, and cycles of life and death. Farmers in many cultures linked planting and harvesting schedules to lunar calendars. Sailors learned to read tides by watching both the moon and the shoreline. We will come back to these cultural and biological rhythms later. For now, it is enough to see that the moon does three major things at once. It pulls the oceans back and forth, sculpting coastlines and mixing waters. It shapes patterns of night light, changing the rules for nocturnal life every few days. It provides a stable, predictable clock in the sky that any creature with eyes or light-sensitive cells can, in principle, learn to follow. In this first part, we have set the stage. We have seen the moon not just as a decoration above Earth, but as a gravitational partner that moves entire oceans and as a rhythmic lantern that pulses through the month. We have hinted at its role in stabilizing Earth's spin and in setting the pace of some biological clocks. In the next part of this story, we will go closer to the water's edge. We will walk through tidal flats, coral reefs, and open coasts to see how specific species have literally built their lives around the moon's pull and light. We will follow crabs, fish, corals, turtles, and plankton as they ride the tides and phases. And we will see that for many of them, the moon is not distant at all. It is as intimate as a heartbeat. To see just how special this relationship is, it helps to rewind the story all the way back to the moon's birth. The leading idea among planetary scientists is called the giant impact hypothesis. In this picture, the very young Earth, still hot and partly molten, was struck by a Mars-sized body often nicknamed Theia. The collision was not a gentle merge. It was violent enough to vaporize and eject huge amounts of rock from Earth's outer layers into orbit. For a while, Earth would have worn a halo of glowing debris. Over time, that debris clumped together under its own gravity, forming one or more moonlets that eventually merged into the single moon we know. Computer simulations show that such an impact can naturally produce a large satellite with an orbit like the moon. And the chemistry of lunar rocks, similar to Earth's outer layers but not identical, fits this picture. If this hypothesis is correct, then the moon is not an alien-captured object. It is made, in large part, from Earth itself. The consequences for life begin immediately. Right after the impact, the moon would have orbited much closer to Earth than it does today. It would have loomed huge in the sky. Tides would have been far stronger, raising and lowering oceans by tens or even hundreds of meters in some places. The day would have been very short, perhaps only a few hours long. As time passed, the system calmed. The moon moved outward. Earth's rotation slowed. The rate of tidal energy loss decreased. But the early, more extreme conditions could have helped mix oceans thoroughly and may have influenced how heat and chemicals were distributed on the young planet. Those distributions, in turn, would have affected where the first stable habitats for life appeared. We cannot go back and watch those events, but we can read some of their traces in rock. The lunar surface, battered by impacts and unprotected by atmosphere or plate tectonics, preserves an ancient record. Craters that are billions of years old still sit where they formed. Dark basalt plains, the lunar maria, mark ancient lava flows that filled large impact basins. The number and size of craters in a region tell us roughly how old that surface is. When astronauts and robotic missions brought back rocks from different parts of the moon, scientists dated them using radioactive decay. The ages they found cluster around key periods in solar system history, including times when impacts were especially common. Those same periods left scars on Earth, but on Earth, much of the evidence has been erased by weathering, erosion, and the motion of continents. The moon acts as an archive for Earth's early environment, including the era when life was just beginning. Even now, the moon's airless surface quietly records information that matters for life. Cosmic rays and particles from the sun strike its regolith, the loose surface material, without being deflected by a magnetic field or atmosphere. Over time, some of those particles become trapped in grains. By studying them, scientists can infer details about solar activity and cosmic radiation over very long timescales. Those same types of radiation affect Earth's atmosphere and, indirectly, climate and life. The moon also has subtle internal activity. It is not geologically dead. Instruments left by Apollo astronauts detected moonquakes, small seismic events caused by tidal forces as the moon flexes under Earth's gravity, by thermal expansion and contraction as the surface goes from lunar day to lunar night, and perhaps by minor tectonic readjustments. These quakes reveal that the moon has a layered interior, crust, mantle, and a small core. The exact structure matters because it affects how the moon responds to Earth's pull and how its orbit evolves. The details of that evolution feed back into how strong tides are on Earth and how quickly Earth's rotation slows. By tracing these chains of cause and effect, you can see a pattern. The moon is not a passive reflector of sunlight. It is an active partner shaped by the same forces that shape Earth, and in turn, it shapes Earth back. The two bodies share a violent origin, exchange energy and angular momentum, and together define the gravitational environment in which life has unfolded. When you look up at the moon now, you are seeing not only a companion in the sky, but also a fossil of an ancient catastrophe that set the stage for everything that followed. Imagine standing on a wide, flat beach at low tide. Hours ago, this area was underwater. Waves broke closer to the dunes. Fish swam over your head height. Now the sea has pulled back. Dark, wet sand stretches far out toward the horizon. Shallow pools glisten in dim starlight and faint sky glow. The air smells of salt, algae, and exposed rock. In the beam of a flashlight, life appears everywhere. Small crabs scuttle sideways across the sand, disappearing into tiny holes the moment they sense vibration. Worms leave winding tracks. Shells are half buried in ripples of sediment. In small pools, miniature worlds remain. Anemones flex, small fish hover, and snails graze on thin films of algae. All of these organisms live at the mercy of the tides. The moon's pull sets the schedule for their feeding, breathing, and hiding. When the tide comes in, they may be submerged in cool, oxygen-rich water. When it goes out, they risk drying, overheating, or overcooling, and exposure to land-based predators. Take barnacles as an example. Barnacles begin life as free-swimming larvae drifting in the water column. When it is time to settle, they glue themselves head first onto a hard surface, rock, pier, even the hull of a ship. They secrete a strong cement and build a hard shell around themselves. Once locked in place, they cannot move again. Their survival strategy is all about vertical position in the intertidal zone. Too low, and they spend most of their time underwater, facing constant competition and more predators. Too high, and they risk long, dry periods during low tide. In many rocky coastal areas, you can see distinct bands of barnacles, mussels, and other species stacked at different heights. Those bands are shaped by the moon's tidal reach and by how well each species tolerates exposure to air. When the tide is high, barnacles extend feather-like appendages to sweep plankton from the water. When it is low, they close their plates tightly to trap a small amount of water inside, waiting out the dry, windy hours. Mussels and oysters use a similar strategy on a slightly different schedule. They cling together in dense beds, attached to each other and to rocks or pilings by tough threads. At high tide, they filter enormous volumes of water, feeding on microscopic plankton. At low tide, they close their shells. If tides were weaker, slower, or irregular, the pattern of feeding and resting that supports their metabolism would change. Entire mussel beds might shift location or fail to form at all. Now move from the muddy shore to a coral reef in warm, shallow water. Coral colonies are built by tiny animals that secrete calcium carbonate skeletons. They host symbiotic algae inside their tissues that perform photosynthesis, feeding both themselves and their coral hosts. Sunlight is crucial here, but the moon also plays a subtle role. Many coral species synchronize their spawning with remarkable precision. For most of the year, each colony of coral reproduces only asexually, by growing and branching. But on certain nights, often once or a few times per year, vast numbers of coral colonies release eggs and sperm into the water simultaneously. The sea turns milky as clouds of reproductive cells drift and mix. This mass spawning dramatically increases the chances that eggs will be fertilized and that new coral larvae will form. How do corals coordinate across such wide areas? They use multiple cues: water temperature, day length, and critically, the phase of the moon. Experiments and observations have shown that in many species, spawning tends to occur a certain number of days after the full moon or around particular lunar phases. The moon's light and gravitational influence provide a reliable, long-term signal. Individual corals do not have brains, but they do have biochemical pathways that respond to tiny changes in light intensity and timing. Some fish also tune their life cycles to the moon. Along certain beaches, during particular seasons, small fish called grunion ride waves onto shore at very high tides linked to full or new moons. Females wriggle into wet sand and lay eggs. Males wrap around them to release sperm. As the tide retreats, the adults slip back into the sea, leaving the eggs buried where ordinary waves do not reach. Those eggs develop in the damp sand. They hatch when the next series of very high tides returns, roughly 2 weeks later, stirred by the moon's cycle. The timing ensures that newly hatched larvae are swept out to sea, where they can begin feeding. Sea turtles, famous for their long migrations and vulnerable nesting, also seem to pay attention to the moon, though their behavior is guided by multiple cues. Adult female turtles crawl onto beaches to dig nests and lay eggs. The timing of these nesting events is influenced by water temperature, tides, and sometimes lunar phase. When hatchlings emerge weeks or months later, usually at night, they find their way to the sea by moving toward the brightest horizon, which in a natural setting is often the moon and stars reflected off the water. Artificial lights on beaches can confuse them, pulling them away from the sea. That modern problem illustrates how deeply their navigation systems are tied to the natural night sky. The moon's influence reaches out beyond dramatic events like mass spawning and nesting. Many marine organisms perform daily vertical migrations in the ocean, rising toward the surface at night to feed and sinking deeper during the day to avoid visual predators. On nights with bright moonlight, some species adjust their depth and timing, staying deeper to remain in relative darkness. Others may use the moon's predictable cycle to fine-tune their behavior, avoiding nights when they would be too visible against the faintly lit surface. Even plankton, tiny drifting organisms that you might think of as passive, can show subtle responses to lunar cycles in their abundance and behavior. The moon also shapes habitats that indirectly support life. Salt marshes and mangrove forests, for example, exist only because regular tides flood and drain coastal areas. In a salt marsh, grasses and other halophytic plants grow in thick mats across muddy flats. When the tide comes in, seawater floods shallow channels and pools, bringing nutrients and small fish. When it recedes, it leaves behind damp sediment rich in organic material. Birds, crustaceans, and small mammals forage in this shifting landscape. Mangrove forests, with their tangle of aerial roots, trap sediment and slow water flow. Between the roots, fish and invertebrates find shelter from larger predators. Juvenile fish often spend their early lives in these sheltered waters before moving to coral reefs or the open sea. The growth and health of these ecosystems depend on the pattern and amplitude of the tides, which in turn depend heavily on the moon. If you follow the tides inland, you see other, more subtle effects. Estuaries, where rivers meet the sea, experience mixing of fresh and salt water that depends on tidal flows. Many fish species, including commercially important ones, use estuaries as nurseries. Larval and juvenile stages move with the tide, finding food and shelter in complex salinity gradients. Changes in tidal strength would change where and how those nurseries function. The moon's gravity also contributes to currents in the deep ocean. Tidal forces cause internal waves to form where water layers of different densities meet, for example at the boundary between warm surface waters and colder, deeper layers. When these internal waves break against underwater ridges or continental slopes, they mix water masses and move nutrients from the deep back toward the surface. This mixing is part of what supports phytoplankton growth. Phytoplankton need light and nutrients. Near the surface, light is abundant but nutrients can be depleted. Deeper down, nutrients are abundant but there is no light. Any process that moves nutrient-rich deep water toward the sunlit layer supports productivity. Lunar tides, though only one of several mixing mechanisms, are a significant contributor. Without this constant, gentle stirring, some regions of the ocean would become more stratified. Productivity would drop. Food webs from plankton to fish to top predators would be altered. Over long timescales, even global cycles of carbon and oxygen could shift. Beyond the water, the moon's light shapes terrestrial life. In forests, deserts, and grasslands, many animals are active mainly at night to avoid daytime heat or predators. For them, the amount of moonlight can change the rules of engagement. On bright nights, predators that rely on vision, like some owls, cats, and foxes, can see better. Prey animals, in turn, may choose to move less or stick to areas with more cover when the moon is high and bright. On very dark nights near the new moon, roles can flip. Some predators that prefer stealth in darkness become more active, while others that need light hunt less. Researchers who place motion-sensitive cameras in wild landscapes often see monthly patterns in activity linked to the lunar cycle. Not every species responds in the same way, but taken together, The behavior of many animals is subtly choreographed by the moon's changing phases. Even plants can feel the moon, though not in ways that are as well understood as their response to sunlight. The tiny gravitational pull that the moon exerts on every object on Earth, including trees and stems, causes small, measurable changes in water movement and tissue tension. Sensitive instruments have detected slow, rhythmic swelling and shrinking in tree trunks that seem to follow tidal cycles, even far from the sea. The biological significance of these patterns is still being explored, but they remind us that gravity flows through living tissues as well as through oceans. Humans have long woven stories and systems around these rhythms. Lunar calendars, based on months of roughly 29 or 30 days, have been used by many cultures. Some religious festivals and cultural events are timed to phases of the moon. Fisher communities in many parts of the world have traditional knowledge about when fish are likely to be more active or when certain species are best caught, linked to tides and lunar cycles. For most of history, before electric light, moonlight was the brightest natural illumination available at night. Travel, hunting, gatherings, and even conflicts were sometimes planned around full moons, when people could see farther. The term, harvest moon, refers to the idea that farmers could work late into the evening harvesting crops by the light of the moon closest to the autumn equinox. In the modern world, city lights drown out much of this connection. From within a bright metropolis, the difference between a full moon and a new moon night may barely register. Artificial lighting makes night almost as bright as day in some neighborhoods, but in more remote areas, and for animals that have not replaced the moon with streetlights, the old patterns remain. In this second part of our story, we have walked from rocky shores to coral reefs, from turtle nesting beaches to mangrove forests, from estuaries to open ocean, and finally back onto land and into human culture. Along the way, one theme keeps repeating. The moon does not act through a single dramatic event. It acts by providing regular, predictable changes in gravity and light. Life has had billions of years to notice those patterns and adapt to them. For many species, from barnacles to corals to fish and turtles, the moon is a fundamental part of their calendar and geography. But the moon does something even more profound than shaping tides and rhythms. It helps stabilize the stage on which all of this plays out, Earth itself. In the next part, we will step back and look at longer timescales and larger systems. We will see how the moon influences Earth's tilt, day length, climate patterns, and even the pace at which life has been able to evolve and spread across the planet. We can also shift perspective from coastlines to the open sea and ask how the moon's pull shapes life far from any shore. In the middle of the ocean, far from continents, there are no dramatic beaches or tidal flats. The difference between high and low tide in sea level can be small, sometimes only a few tens of centimeters. Yet even here, tides matter, less as visible changes in height and more as patterns of motion and mixing. Imagine a column of water a few kilometers deep. At the surface, wind and waves stir the upper layers. Sunlight penetrates, fueling photosynthesis in tiny phytoplankton. Below a certain depth, called the euphotic zone, light fades. Deeper waters are colder, denser, and often richer in nutrients but too dark for photosynthesis. Tidal forces passing over rough seafloor features, such as mid-ocean ridges and underwater mountains, generate internal waves that propagate along the boundaries between water layers of different densities. These internal tides can be hundreds of meters tall, though they are invisible from above. When they travel into regions where conditions are right, they break, like surf on an underwater beach, dumping their energy into turbulence. That turbulence mixes water from different depths, carrying nutrients upward and oxygen downward. Phytoplankton near the surface then benefit from the new nutrient supply. They grow and divide, forming the base of food webs that support zooplankton, fish, squid, whales, and seabirds. Carbon taken up by phytoplankton during photosynthesis can eventually sink as organic matter, helping regulate Earth's climate by moving carbon dioxide from the atmosphere into the deep ocean. In this way, the Moon's gravity reaches all the way into global carbon and oxygen cycles. Not by a single dramatic gesture, but by countless tiny nudges that accumulate as mixing events over vast areas and long periods. Life in the deep, dark ocean also feels the Moon indirectly. Some deep-sea animals time their spawning to match cycles of sinking food from the surface, which can be influenced by surface blooms tied to light and mixing. Others may respond to minute changes in pressure associated with tides, especially in regions where tidal ranges are larger. Research at great depths is difficult, but every new set of observations seems to reveal more ways in which rhythms from above penetrate the darkness. For humans who work at sea, tides remain a daily, practical concern. Ship captains plan harbor entries and departures around high water to avoid grounding. Divers consider tidal currents when planning underwater work so they are not swept away. Offshore engineers designing wind farms, oil platforms, or floating structures must calculate tidal forces and currents precisely to ensure stability and safety. Recreational activities, too, are tuned to the Moon without most participants explicitly thinking about it. Surfers pay attention to tides because they change wave shape and break points. Sea kayakers and small boaters learn where tidal races, fast currents between headlands or islands, form, and how to use or avoid them. Wildlife watchers plan trips to see feeding frenzies where tidal currents concentrate fish. Behind all of this, the Moon keeps pulling second by second, unnoticed but indispensable. If you could magically turn off the Moon's gravity for a while, leaving everything else unchanged, you would see the difference quickly at sea. Tidal currents would slacken. The timing and strength of mixing events would change. Some nutrient pathways would slow. Over time, productivity patterns would shift. Certain fishing grounds might become less reliable. Some breeding strategies in coastal and pelagic species would no longer work as well. Life would adapt, but the adjustments would ripple through entire food webs. The Moon does not simply cause life in the ocean, but it strongly shapes where life is most abundant, where it can safely reproduce, and how energy and matter flow between different parts of the marine system. To understand how deeply the moon controls life on Earth, we have to go beyond beaches and bright nights. We have to look at the planet as a spinning, tilted sphere of rock and water moving through space. Start with Earth's rotation. Today, Earth takes about 24 hours to spin once relative to the Sun. That spin gives you day and night. It shapes wind patterns, ocean currents, and the behavior of the atmosphere through the Coriolis effect. It sets the basic rhythm that many organisms use for their internal clocks. But Earth did not always spin at this speed. Billions of years ago, shortly after the moon formed, Earth rotated much faster. One common estimate suggests that a day on the early Earth might have been only 6 to 10 hours long. The moon was also much closer then, looming larger in the sky and exerting stronger tidal forces. Over time, the gravitational interaction between Earth and Moon has traded rotational energy for orbital distance. As the Moon raises tides on Earth, those tidal bulges do not line up perfectly with the line connecting Earth and Moon. Because Earth rotates, friction between the moving water and the planet's surface drags the bulges slightly ahead of the Moon's position. That misalignment means the bulges exert a small forward pull on the Moon, adding energy to its orbit. The result is that the Moon slowly spirals away from Earth, and Earth's rotation slows down. Today, precise measurements using laser beams bounced off reflectors left on the Moon's surface show that the Moon is receding at a rate of a few centimeters per year. Over millions of years, this adds up. Fossil growth patterns in ancient corals and other organisms suggest that hundreds of millions of years ago, there were more days in a year than there are now. The length of the day has been increasing as the Moon moves outward. Why does this matter for life? Consider circadian rhythms. Many organisms, including humans, have internal clocks that run on roughly 24-hour cycles. These clocks regulate sleep, feeding, hormone release, and many other processes. They are synchronized to the external day-night cycle by light, primarily sunlight. If Earth had a very different rotation period, say 10 hours or 40 hours, life would have evolved with different internal schedules. The slow, regular lengthening of the day, due to the Moon's braking effect, has given life time to adjust. There is no abrupt shift that would disrupt biological rhythms. Instead, over millions of years, clocks can tune themselves generation by generation. The Moon, by influencing Earth's rotation, has indirectly shaped the temporal framework in which life's daily patterns operate. Now look at seasons. Earth's axis is tilted by about 23.5 degrees relative to the plane of its orbit around the Sun. This tilt is why you have seasons. When the northern hemisphere is tilted toward the Sun, it experiences summer. Longer days, higher sun angle, more direct sunlight. 6 months later, it is tilted away, producing winter. The southern hemisphere experiences the opposite pattern. If Earth's tilt were to swing wildly over time, the distribution of sunlight across latitudes would change dramatically. Some planets are like this. Mars, for example, does not have a large moon to stabilize its tilt. Over long timescales, its axial tilt can vary significantly, perhaps between values close to 0 and values greater than 40 degrees. That kind of variation would cause extreme climate swings, with polar regions sometimes receiving much more sunlight than they do now, and sometimes much less. Earth's tilt also changes, but far more gently. The presence of a relatively large moon helps stabilize it. The details involve interactions between the gravitational pulls of the Sun, Moon, and other planets on Earth's equatorial bulge. The Moon's strong torque on that bulge damps out some of the larger variations that would otherwise be possible. As a result, Earth's axial tilt does wobble, but within a limited range, roughly between 22 and 24.5 degrees over cycles of tens of thousands of years. These modest changes are enough to drive the ice age cycles of the last few million years when combined with shifts in Earth's orbit. But they are not so extreme as to make the planet regularly flip between radically different global states. For life, that relative stability is a gift. It means that climates, while variable, stay within certain bounds for long enough that complex ecosystems can evolve and persist. Tropical forests are not regularly replaced by polar deserts and then back again. Ice sheets do not repeatedly extend to the equator and then vanish on timescales so short that evolution cannot keep up. Geologists and astrobiologists have asked an intriguing question. Would complex life, as we know it, have had time to develop on Earth if the Moon did not exist? It is impossible to run a controlled experiment with a second Earth, but climate models suggest that without the Moon's stabilizing influence, Earth's tilt might have wandered more dramatically. That could have produced more chaotic climate changes. Life might still have arisen. Microbes are remarkably resilient. But the path toward large, complex, land-based organisms might have been very different or slower. The Moon's control extends into the deep past in another way. By sculpting early coastal and shallow water environments that may have been crucial for the transition of life from sea to land. Imagine Earth, a few 100 million years after life first appears in the oceans. The continents are barren or nearly so. Shallow seas lap against rocky shores. Microbial mats coat some surfaces. Tides, driven by a closer moon and a faster spinning Earth, are stronger than they are today. Twice per day, water surges far up onto the land and then retreats far back, leaving behind pools and films of seawater. In these tidal flats and pools, organisms experience extreme changes over short distances. A microbe or early multicellular organism might find itself alternately submerged, damp, and almost dry. Salinity shifts as pure rainwater mixes with seawater and then evaporates. Temperature swings between cold nights and hot days. Oxygen levels fluctuate. These fluctuating environments create strong selective pressures. Organisms that can survive temporary exposure to air have an advantage. Those that can tolerate changes in salt concentration and temperature are favored. Over time, structures and behaviors that help in these conditions, protective coverings, ways to retain moisture, simple forms of movement, become more common. Some hypotheses about the origin of land plants and animals emphasize these tidal zones as likely training grounds. From there, early lineages could move gradually farther from the sea, bringing with them the tools they evolved under the moon's pulsing influence. Roots, waxy coatings, limbs, lungs, and other features we now take for granted may trace their evolutionary roots back to ancestors that first faced the challenge of a world that was intermittently wet and dry because of tides. The moon also contributes to the pace at which Earth's interior and surface exchange material. Tides do not only affect water. Solid Earth tides, subtle flexing of the crust and mantle under the changing gravitational pull of the moon and sun, also occur. On most days, you cannot feel or see these deformations, but sensitive instruments can measure them as small rises and falls in the ground. Over long periods, this rhythmic flexing may influence how easily faults slip, how magma moves, and how heat escapes from the interior. The effect is not huge compared to other forces like plate motion and internal convection, but it is real. In a subtle way, the moon helps keep Earth's interior and surface in conversation, which matters for long-term climate, nutrient cycling, and the habitability of the planet. Another place where lunar control shows up is in the behavior of Earth's atmosphere and oceans as a coupled system. We have already talked about tidal mixing, but there is also evidence that lunar cycles can modulate certain atmospheric phenomena. In some data sets, small but measurable lunar signals appear in rainfall patterns, atmospheric pressure, and even lightning rates. These effects are tiny compared to those driven by solar heating and large-scale weather patterns, but they illustrate that the moon's influence threads through the entire Earth system, from core to crust to ocean to air. For most organisms, this control is not conscious. Plants do not know that the moon is stabilizing Earth's tilt. Fish do not know that the length of the day has increased over hundreds of millions of years because of tidal friction. Microbes in deep rock do not know that lunar cycles nudge the crust they inhabit. Yet, their entire worlds, the range of temperatures, salinities, and pressures they experience, are shaped by processes in which the moon plays a part. Humans are unusual in this story. We have the ability to trace these connections scientifically. We can reconstruct past day lengths by counting growth rings in fossil corals. We can simulate the effect of changing axial tilt on climate with computer models. We can measure the moon's recession with lasers and mirrors. We can feel the tides and then calculate with equations how much energy is being transferred between Earth's rotation and the moon's orbit. That knowledge lets us see the moon as something other than a passive ornament. It is an active participant in Earth's story, even if its actions are slow and gentle compared to storms, earthquakes, and volcanic eruptions. In this third part of our journey, we have seen the moon as a regulator on very long time scales. It sets the pace of Earth's spin. It helps keep Earth's tilt within a life-friendly range. It amplifies and shapes tides that may have helped life move from water to land. It flexes the solid Earth and modulates subtle features of atmosphere and ocean. All of this is control in a physical sense, not in the sense of intention. The moon does not choose. It simply exists where it does, with the mass it has, and the laws of gravity and motion do the rest. Life has emerged and evolved within that framework, adapting to conditions that the Earth-Moon system together provide. There is one more layer to add, the layer of human perception and meaning. For tens of thousands of years, humans have told stories about the moon. Some of those stories describe it as a deity, a watchful eye, a trickster, or a calendar. Others link it, rightly or wrongly, to madness, fertility, or fate. In the modern era, we have walked on its surface, brought back samples, and placed instruments that quietly report back to us. In the final part of this story, we will focus on that intersection between physical control and human life. We will ask how the moon affects human bodies and minds, what science says about sleep and mood, how myths of lunar influence compare with data, and how our relationship with the moon might change in a future where we live both on Earth and perhaps on the moon itself. When scientists try to reconstruct how the Earth and Moon partnership has affected life over billions of years, they turn to natural archives that record both time and environment. One of the most intriguing of these archives lies in the growth patterns of ancient organisms. Some corals, clams, and stromatolites, layered structures built by microorganisms, lay down daily and seasonal growth bands in their skeletons or shells. Under a microscope, these bands can be counted and measured much like tree rings. In some very old fossils, scientists have found evidence of many more daily bands per annual cycle than we see today. This suggests that in those ancient times, days were shorter and years contained more rotations. For example, corals from hundreds of millions of years ago appear to record years with over 400 daily layers, implying day lengths of around 20 hours. The trend across many such samples is consistent with the idea that Earth's rotation has been slowing gradually as tidal friction with the moon drains rotational energy. These fossils, in other words, are not just records of individual organisms. They are clocks that remember how long days used to be. Combining this information with models of tidal evolution helps researchers trace how the strength of tides, the distance to the moon, and the length of days have co-evolved. Those changes, in turn, influenced when certain habitats became available, how much time organisms had for daily tasks like feeding and repairing tissues, and how internal clocks were tuned. Glacial deposits and sediment layers also carry subtle signatures of orbital and axial cycles. In sequences of rock that span millions of years, patterns in layer thickness and composition can match the frequencies of known Milankovitch cycles. These patterns reveal how shifts in Earth's orbit and tilt have paced ice advances and retreats, sea level changes, and shifts in climate zones. The moon's stabilizing influence on tilt is encoded in these records as well, because it shapes the amplitude and regularity of the cycles. By interpreting these patterns, scientists can reconstruct not only physical climate, but also some aspects of how life responded. When reefs expanded or contracted, when certain plant types spread, and when deserts advanced or retreated. This long view emphasizes that the moon's control over life is not something that switched on at a particular moment. It has been present in one form or another since before the first recognizable plants colonized land, before vertebrates walked on four legs, before insects took flight. It has always been part of the background conditions, sometimes quietly supportive, sometimes amplifying other changes. At certain key transitions, that support may have been critical. During times when Earth's climate teetered between very cold and more temperate states, a relatively stable tilt could have provided refuges where life could persist until conditions improved. During the colonization of land, strong but predictable tides would have created zones where organisms could gradually adapt to air exposure. During the diversification of ecosystems, regular seasons would have allowed reliable cycles of growth and reproduction. Seen this way, the moon has been like a quiet stagehand in a vast theater. It does not write the script or play the lead roles, but it makes sure the lights rise and fall on cue. The set does not collapse, and the floor does not tilt too wildly under the actor's feet. Without that stagehand, the play might still happen, but with more interruptions, more chaos, and perhaps fewer complex scenes. Understanding this deep history also changes how we think about the future. As humans alter the climate through greenhouse gas emissions and land use, we are effectively adding a new, fast layer of change on top of the slower, moon-influenced cycles. The moon will still stabilize Earth's tilt. Tides will still move water and mix nutrients. But the baselines of temperature, ice cover, and sea level will shift more rapidly than many ecosystems are used to. By knowing how past life responded to slower, natural changes, we gain a frame of reference for judging the pace and risks of current changes. The moon's presence does not protect us from the consequences of our own actions, but it does mean that some elements of the planetary system, day length, tilt range, tidal rhythm, will remain predictable even as other aspects change. That predictability can be an anchor for planning adaptation. Coastal communities, for example, will still be able to rely on accurate tide predictions even as average sea level rises. Migratory species that use moonlight and tides as cues will still find those cues where they have always been, even if they encounter new temperatures or altered food availability along their routes. The challenge for humans is to respect both the stability and the sensitivity of the system we inhabit. When people say the moon controls us, they often mean something very specific and very human. They might be thinking of legends about full moons driving people mad, increasing crime, or triggering births. They might picture wolves howling, tides surging, and emergency rooms filling with strange cases when the moon is round and bright. So far in this journey, we have seen that the moon really does control many aspects of life on Earth. Tides, rhythms, climate stability, and deep evolutionary processes. But what about the direct effect on human bodies and minds? To answer that, we need to separate three things clearly. First, the physical forces the moon actually exerts. Second, the measurable biological responses in humans and other animals. Third, the stories we tell about those forces and responses. Start with the forces. The gravitational pull of the moon on an individual human body is incredibly small. You might be more strongly affected, in a strictly gravitational sense, by a nearby building or hill. Where the moon's gravity truly matters is at large scales, where tiny differences across long distances can move ocean basins of water. The light from the moon is also gentle. At its brightest, a full moon is still hundreds of thousands of times dimmer than the midday sun. Yet in the context of a natural night, that soft light is enormous. It is enough to cast clear shadows, to illuminate landscapes, and to change how easy it is for animals to see each other. Biologically, humans are sensitive to light, especially in a specific range of wavelengths that influence our circadian clocks. Our eyes contain not only rods and cones for vision, but also special light-sensitive cells that send signals directly to the brain regions that manage sleep and wake cycles. Even fairly low levels of light at night can shift the timing of these cycles. In a world lit only by fire and celestial bodies, the moon's light would have been a major contributor to nighttime illumination. Some studies have suggested that human sleep patterns show small variations with the lunar cycle. In certain experiments, people seem to fall asleep slightly later and sleep a bit less deeply around the full moon, even when they are not consciously aware of the moon's phase and when light levels are controlled. Other studies fail to find consistent effects. The results are mixed and often subtle. What these data likely tell us is that if the moon has a direct influence on human sleep, it is modest compared to artificial light, work schedules, and personal habits. Modern humans live in environments flooded with electric light. Screens, lamps, and streetlights vastly overpower the moon's glow in most built spaces. Shift work, social activities, and global communication patterns dictate when many people sleep more than the moon does. The stronger lunar influences show up in non-human animals that still live under natural night skies. As we saw earlier, the foraging behavior of many nocturnal species shifts with the lunar cycle. Prey animals may avoid bright, open spaces during full moons, while predators that rely on vision may hunt more. Some insects adjust their movements. Amphibians may call more or less depending on how easily they can be seen. In that sense, even if the moon's direct effect on you is muted by technology, it is still actively controlling life in forests, deserts, and oceans. Now consider the stories. For centuries, people have linked the moon to madness, giving rise to words like lunacy and lunatic. Folklore and anecdote often claim that more unusual behavior, crime, or accidents occur during full moons. Many medical staff, police officers, and emergency workers report a subjective feeling that their work is busier or stranger on those nights. When researchers gather large data sets and examine them statistically, the picture becomes less dramatic. Most careful studies do not find strong, consistent increases in crime, psychiatric admissions, or emergency room visits that line up cleanly with the lunar cycle. Where small effects are found, they can often be explained by other factors, such as weekends, holidays, or social behaviors that happen to coincide with certain lunar phases. This does not mean that people are lying when they say full moons feel intense. Human memory is selective. Dramatic events are easier to recall than quiet nights. If you believe that full moons are special, you are more likely to notice and remember unusual events when the moon is bright and to forget similarly unusual events on darker nights. This is a kind of cognitive bias, not a failure of intelligence. The real, measurable powers of the moon are spread out in time and space. They appear in the shape of coastlines, the distribution of nutrients in the sea, the long-term stability of climate, the timing of animal migrations and reproduction, and the evolution of day length. These are subtle, slow, and often invisible to casual human observation. Myths tend to cluster instead around things that are obvious to our senses. The striking appearance of a full moon, the eerie quality of its light, and the psychological impact of a bright disk watching you from the sky. There is another reason the moon feels like it controls us more than it actually does in a direct, immediate sense. The moon is one of the few celestial objects whose motion you can easily see change with the naked eye from night to night. You can watch it rise in different places along the horizon, change phase, and drift among the stars. It feels close and active. In contrast, the sun seems steady and unchanging, even though it is vastly more powerful. Planets move slowly and stars appear fixed. The moon, with its visible motion and changing face, invites projection. In modern times, our relationship with the moon has added a new chapter: exploration. Humans have walked on its surface. 12 astronauts across several missions left boot prints, flags, and equipment on that airless world. Robotic spacecraft from multiple countries have orbited, mapped, and landed on it. Some have deployed instruments to measure moonquakes, heat flow, and the properties of lunar dust. These missions transformed the moon from a distant light into a place. We have measured its composition, density, and internal structure. We have tested models of its origin, most of which point toward a violent beginning, a collision between the early Earth and a Mars-sized body, ejecting debris that eventually coalesced into the moon. That origin story matters for life. If the moon was born from such a collision, it likely formed hot and close. Its presence would have influenced Earth's rotation and tilt from very early in the planet's history. The tides from a closer, larger appearing moon would have been even stronger. The interaction between Earth and moon may have helped strip away some of the earliest atmosphere, shaping surface conditions in ways that mattered for emerging life. Looking ahead, we can imagine a future in which the moon becomes more than a background influence. It could become a place where humans live. Permanent or semi-permanent bases on the moon have been discussed by engineers and space agencies for decades. Such bases would exist in an environment very different from Earth's: low gravity, extreme temperature swings, no air, and skies that are always black. Yet, they would also sit at the intersection of two gravitational wells, orbiting Earth while orbiting the Sun. Life in such a habitat would depend on technology, in ways even more extreme than life, in our thought experiments: underground refuges on a dark Earth. Air, water, and temperature would be entirely controlled by human systems. Food would need to be grown in sealed modules or delivered from Earth. Radiation from the sun and cosmic rays would require shielding. The rhythms of day and night would be replaced by the roughly 29.5-day lunar day cycle, unless habitats used artificial lighting schedules. Ironically, people living on the moon would be looking back at Earth as their primary source of stability. They would watch Earth rise and set in their sky over the course of a lunar day. They might use signals from Earth-based clocks and satellites to keep time. Their sense of home might be tied to a blue-white sphere in their sky, even as they themselves stand on the gray dust of a world that has controlled Earth for eons. Over very long timescales, the relationship between Earth and Moon continues to change. As we have seen, the Moon is slowly moving away and Earth's rotation is slowing. Hundreds of millions of years from now, days will be longer by noticeable amounts. The apparent size of the Moon in the sky will shrink. Total solar eclipses, in which the Moon perfectly covers the Sun, will eventually no longer occur. The Moon will appear too small, producing only annular or partial eclipses. The tides will weaken slightly as distance increases, changing the balance of forces that shape coastlines and mixing. The stabilizing influence of the Moon on Earth's tilt will remain, but the details of precession cycles and climate patterns will evolve. At the same time, the Sun will be continuing its own slow brightening toward a hotter future. In that distant era, long before the Sun becomes a red giant, Earth's climate will be changing for reasons unrelated to human activity. The interplay between a brighter Sun, a slower spinning Earth, a more distant Moon, and evolving life will produce a world very different from the one you know. In this long view, control becomes a network of mutual influences. The Moon shapes Earth's rotation and tides. Earth shapes the Moon's orbit and internal activity. The Sun shapes both Earth and Moon through its gravity and light. Life responds to these influences and, in turn, alters the atmosphere, the chemistry of the oceans, and the reflectivity of the surface. You live inside that network, usually without feeling the threads. When you look at the Moon, you are seeing not just a pretty object, but a piece of machinery in the Earth system. It is a moving weight that pulls on oceans, crust, and air. It is a stabilizer that keeps Earth's tilt within a safe range. It is a soft lantern that has guided animals and humans for countless nights. It is a timekeeper that has sliced history into months and guided calendars and rituals. At the same time, you are seeing a world that we have touched with our technology and imagination. Its surface bears traces of ancient impacts and recent footprints. Its craters record billions of years of solar system history. Its rocks have preserved information about early solar conditions that Earth itself has long since erased with plate tectonics and erosion. The phrase "how the Moon controls life on Earth" can sound dramatic, almost mystical. But the real story is more interesting than simple magic. The Moon controls life not by issuing commands, but by shaping the physical conditions under which life operates. It raises tides, sets rhythms, steadies the planet's tilt, and participates in slow exchanges of energy and angular momentum. Life, including human life, has taken those boundary conditions and built astonishing complexity within them. As you finish this story, you might step outside on a night when the moon is visible. You can notice how its light falls on buildings, trees, or clouds. You can think about the invisible pull it exerts on the oceans, slowly moving water on shores far away. You can remember that the length of the day you experience, the stability of the seasons you live through, and even some of the early opportunities that allowed life to colonize land are linked to this silent companion. You can feel, perhaps, a quiet gratitude for a world that is not alone. Earth is not a solitary planet wandering in space. It is part of a pair, locked in a gravitational dance that began with violence and has matured into a kind of partnership. In that partnership, with the sun providing light and the moon providing pull and stability, life has found room to arise, adapt, and wonder. The moon does not know that you exist. It has no awareness of tides, corals, turtles, forests, or human minds listening to narrations about orbital mechanics. But you can know the moon. You can learn how it works, how it shapes your world, and how it fits into the larger universe. And knowing that, the next time you see its pale disk above the horizon, you may feel that the sky is not just beautiful but intelligible, a vast, moving system of which you and the moon and life on Earth are all parts. When you weave together all these threads, oceans, climate, ecosystems, fossils, human culture, and space exploration, a picture emerges of the moon as a quiet orchestrator in the background of life on Earth. Its influence is rarely absolute. Instead, it acts by nudging probabilities and shaping patterns. A turtle hatchling has a better chance of reaching the sea because the moon helps set the timing of tides and the brightness of night skies. A coral reef has a better chance of rebuilding after disturbance because the moon provides reliable cues for synchronized spawning. A forest has a better chance of persisting through millions of years because the moon keeps seasons within a certain range of regularity. At the same time, individual stories are never guaranteed. Storms can still destroy nests. Heat waves and pollution can still stress corals. Human actions can still fragment forests. The moon provides the stage and some of the timing, but not the outcomes. For humans, the moon's role as both object of study and partner in habitability offers a kind of mirror. We now understand enough physics to predict its motions with high accuracy, enough geology to read its history, and enough biology to see how its cycles shape living systems. That understanding gives us power, the power to land spacecraft, to design tidal energy systems, to plan coastal infrastructure, and to protect species that depend on lunar rhythms. It also brings responsibility. Knowing that certain animals rely on dark beaches and natural horizons to navigate, we can choose to reduce artificial lights along nesting coasts. Knowing that tidal wetlands buffer storm surges and store carbon, we can choose to preserve and restore them rather than filling or draining them. Knowing that our own bodies respond to light at night, we can design cities that respect our circadian health. In each of these choices, we are not fighting the moon's control, but aligning ourselves more intelligently with it. On a more personal level, the moon can serve as a reminder of continuity. No matter how complex human society becomes, no matter how many screens and machines mediate our lives, the same moon that pulled on ancient seas and guided early migrations still rises and sets. The same phases wax and wane. The same gravity lifts and lowers the oceans. Stepping outside to notice that fact, even briefly, can reconnect you to a timescale much larger than daily routines. You can think back over the deep time story we have traced. A giant impact, a molten Earth, a forming moon, long ages of cooling and bombardment, the first oceans, tiny organisms learning to thrive in tidal zones, plants greening the continents, animals exploring land, air, and sea, humans learning to count days, months, and years by watching celestial motions, and finally, rockets arcing through space toward the very world that has been shaping ours all along. You live at a moment when this entire chain is visible to you in outline. You can look at a tide chart, a climate model, a fossil coral, a photograph from orbit, and a myth from an ancient culture, and recognize that they are all, in their different ways, expressions of the same underlying relationship between Earth and Moon. That recognition is itself a kind of control, a mental one. It means you are no longer simply carried along by lunar influences unconsciously. You can anticipate them, plan around them, and make decisions that take them into account. You can tell stories that are grounded not only in wonder but also in understanding. In the end, asking how the moon controls life on Earth leads to a deeper, more precise question. How does a simple set of physical laws, acting through a particular arrangement of rock, water, air, and light, give rise to a world where creatures can feel, think, and ask such questions at all? The moon is one piece of that arrangement. It is not the largest, the hottest, or the most complex, but it is uniquely placed to bridge the gap between celestial mechanics and everyday experience. It turns abstract gravity into visible tides, invisible orbital resonances into visible phases, and distant cosmic history into a familiar face in the sky. The next time you script a story, record a narration, or simply pause under the night sky, you can remember that behind every quiet scene, there is this deeper structure. A blue planet, a gray moon, a star, and the laws of physics tying them together in a dance that has made life not only possible, but richly structured and aware enough to tell its own story. Before we close, it is worth pausing for a slower, more deliberate look at what this all means for you, listening right now. Every system we have talked about in this story, from tides and moonlight to climate stability over millions of years, runs on laws of physics that do not care whether anyone is watching. Gravity would still pull, rock would still fracture, water would still flow, the moon would still circle Earth. Yet the fact that you are here, able to think about these things and feel something about them, adds a new layer that is just as real. Your own body carries traces of lunar influence even if you have never lived by the sea. Hormones in your brain are tuned to cycles of light and dark. Your sleep quality changes when your nights are filled with artificial light that ignores the gentle waxing and waning of the moon. The timing of your meals, your work, and your rest still ultimately rests on a planet whose spin and tilt have been shaped by its companion in the sky. Your culture also carries lunar fingerprints. The words for month in many languages come from the moon. Holidays and traditional events are often scheduled by lunar or lunisolar calendars, even if the official calendar on your phone is solar. Stories you heard as a child about the moon, whether scientific or mythical, shaped how you imagine distance, change, and cycles. When you hear that coral reefs spawn under certain phases, or that sea turtles wait for particular combinations of tide and darkness, you are hearing about other species that have turned the moon into a kind of clock. When you hear that Earth's tilt is held within a safe range that prevents chaotic swings in climate, you are hearing about a silent protection that has made long, complex evolutionary stories possible. In a very real way, part of what the moon controls on Earth is the space in which meaning can accumulate. It keeps environmental rhythms within ranges where memory matters, where experience can be passed from one generation to the next, and where behaviors tuned to regular cycles can pay off. This is true for barnacles and birds, but it is especially true for humans, who build not only habits but science, art, and technology on top of environmental patterns. The calm certainty that the moon will rise again, that tides will return, that seasons will follow one another in a familiar order, has allowed people to build calendars, agriculture, navigation, and eventually global civilization. Now, with satellites and sensors, we can see details of the Earth, moon dance that previous generations could only guess at. We can measure tiny changes in the moon's distance with lasers, watch tides from orbit, and calculate how much energy is lost as heat in the oceans each day. We can also see how sensitive many ecosystems are to even small changes imposed by us. Holding these two views together, the ancient and the modern, gives this story its weight. On one side, there is a feeling of reassurance. The moon has been a steady partner across deep time, and its pull continues to shape the conditions that make life possible. On the other side, there is a reminder of responsibility. Knowing how finely tuned some of these conditions are, we can choose whether to push them gently or to shove them hard. As you listen to the final moments of this narration, you might imagine standing at a shoreline under a clear night sky. Waves roll in and out with the tide. The moon hangs above the horizon, reflected in the moving water. Somewhere offshore, plankton are rising toward the surface. Somewhere on the beach, small animals are foraging between rocks. Somewhere far inland, trees are drawing water from soil whose seasonal cycles are set by a stable tilt. Somewhere in the deep past, a giant impact has already launched the moon into the sky. Somewhere in the future, humans may be walking on its surface as easily as they now cross oceans. All of those scenes are connected by a single, simple fact. Earth has a moon, and that moon matters. Once you see that connection, it is hard to unsee it. The sky becomes not just a backdrop, but part of the machinery of life. And the moon, which you may have known only as a beautiful light at night, becomes something more. A quiet architect of the world you live in, and a reminder that even very distant, very slow processes can shape every moment of your own, very local, very human life. There is another way to appreciate how the moon controls life on Earth. By following the trail of clocks inside living bodies, all the way from molecules to behavior. Every living thing needs some way to tell time. For a single bacterium drifting in the ocean, time might simply be the difference between day and night, sensed through changes in light or nutrients. For a plant, time includes daily cycles of opening and closing leaves, and seasonal cycles of flowering and fruiting. For an animal, time includes sleep and wake, feeding and fasting, migration and breeding. All of these processes depend on rhythms that line up with regular patterns in the environment. The most familiar of these rhythms is the daily one. On Earth, the 24-hour cycle of light and dark produced by rotation is such a strong and reliable signal that life has evolved internal clocks, called circadian clocks, that run close to that length. These clocks are not just vague feelings. They are built from networks of genes and proteins that activate and inhibit each other in repeating loops. In humans and many other animals, there is a central clock in the brain, in a region called the suprachiasmatic nucleus. This cluster of neurons sits just above the crossing of the optic nerves. Special light-sensitive cells in the eye send signals directly to it, telling it when it is day and when it is night. The central clock then coordinates many other clocks throughout the body. It influences when you feel sleepy or alert, when your body temperature is highest, when hormones like melatonin and cortisol rise and fall, and even how your digestion and immune system behave at different times of day. Most research on these clocks focuses on sunlight, because it is the dominant source of light and the main driver of daily cycles. But the moon's regular pattern of brightness across the month adds another layer of timing. In many marine organisms, there are internal clocks that run on roughly monthly or twice-monthly cycles. These are sometimes called circalunar or circadian rhythms. They are not simply driven in real time by external forces. Instead, they can keep ticking for a while even when environmental cues are removed, much like a wristwatch keeps going when you put it in a dark drawer. Experiments with certain worms, crabs, and fish have shown that they can maintain rhythms of activity, feeding, or reproduction that match tidal or lunar cycles even under artificial conditions. These internal timers are then fine-tuned and synchronized by actual changes in tide or moonlight. The details differ from species to species. Some appear to have separate sets of genes and molecular loops for daily and for longer rhythms. Others seem to modify a single core clock to respond to both cycles. In all cases, what matters is that life has found ways to encode not just the beat of the day, but the slower beats of the moon. Humans do not have a clearly identified molecular clock that runs exactly on the lunar month in the way some marine species do. However, the human brain and body are still sensitive to light at night, including moonlight in natural environments. Before electric lighting, bright full moon nights would have been the only times when large groups of people could reliably see each other at a distance in open landscapes after sunset. It is plausible that certain cultural behaviors, such as nighttime gatherings, storytelling, or travel, became loosely linked to these bright nights in many societies. Over centuries, such patterns can harden into traditions and calendars. Festivals held at particular full moons in spring or autumn then reinforce the importance of those phases, independent of the original practical reasons. The calendar becomes both a record of environmental cycles and a cultural structure in its own right. The moon's control in this sense operates at three levels at once. At the physical level, it pulls on oceans and slightly on the land and air. At the biological level, organisms evolve internal clocks and behaviors that match the opportunities created by those physical cycles. At the cultural level, humans notice these patterns and turn them into stories, rituals, and systems of timekeeping. None of these levels cancels the others, they stack. Another angle on lunar influence comes from thinking about navigation. Many animals need to know not only what time it is, but where they are and where they are going. Birds migrating across continents use a combination of cues: the position of the sun, the pattern of stars, the Earth's magnetic field, landmarks on the ground, and wind patterns. Some species also appear to use the moon. Certain seabirds, for example, feed at night in open ocean and may use moonlight to help locate prey that migrate toward the surface when it is dark. Others use the brightness and position of the moon to orient themselves relative to coastlines or nesting sites. Insects such as moths sometimes navigate by keeping a constant angle to distant light sources, a strategy that works with the moon but can lead them astray around artificial lights. Sea turtles, as we have already noted, use the brightness of the seaward horizon, enhanced by the reflection of moonlight on waves, as a guide when they hatch and rush toward the ocean. In all of these cases, the moon's role is not to dictate a path, but to provide a stable reference in the sky. If a creature evolves a rule such as move toward the brightest low light on the horizon, or keep the bright disk at this angle to my left, that rule will work night after night in a world where the moon and stars follow predictable paths. When artificial lights are added, or when horizons are blocked by buildings, those rules can fail. The fact that they fail in modern settings is a clue to how strongly they depended on natural, lunar-dominated skies in the past. For humans, the stars have historically been more important than the moon for long-distance navigation, because the moon moves quickly relative to the star background. However, the moon still played supporting roles. Sailors could use its phases to estimate date and approximate tidal conditions in regions they knew well. Observers could time certain events by noting when the moon crossed known stars. Early astronomers used lunar eclipses as time stamps visible across different locations on Earth, helping them refine estimates of longitude and the size of the planet. Even today, satellite navigation systems that seem completely detached from the moon rely on physics first understood by watching celestial motions, including those of the moon. The orbits of navigation satellites must account for gravitational influences from Earth, the moon, and the sun. Their clocks must be corrected for relativistic effects that were tested in part by studying how gravity affects light and time close to massive bodies. The conceptual tools that let engineers build these systems evolved from centuries of watching the moon and planets and asking why they move as they do. In a subtle way, then, the moon has guided not just the movement of animals and water, but the development of human knowledge. By presenting a simple, bright, and nearby example of orbital motion, it invited mysteries that could be solved. Its phases and eclipses forced thinkers to abandon flat Earth models and to adopt a more accurate view of a spherical world lit by a distant sun. Those conceptual shifts, in turn, opened the door to understanding gravity, inertia, and the broader architecture of the solar system. Once humans understood that Earth is one planet among many, and the Moon is one satellite among many, it became possible to imagine other worlds where life might exist. That brings us to another extension of our story: how the presence or absence of a large moon might affect the chances for life elsewhere. When astronomers discover exoplanets, planets around other stars, they often ask questions shaped by our experience with Earth. What is the planet's size and mass? Is there liquid water on its surface? Does it lie in a region around its star where temperatures could allow that water to remain liquid? Does it have an atmosphere, and if so, what is in it? But sometimes, the presence of a large moon is also considered. A massive satellite could stabilize a planet's tilt, as our moon does. It could generate tides that stir oceans, promoting nutrient mixing. It could provide a secondary light source at night, creating additional temporal structure for life. On the other hand, too many or too close moons might produce extreme tides and chaotic variations in spin. We do not yet have the technology to routinely detect Earth-sized moons around distant planets, though a few candidates have been suggested. As observational tools improve, scientists hope to learn whether Earth's combination of one large moon and one medium star is common or rare. If it is rare, that would highlight even more strongly how particular our own situation is. If it is common, it would broaden the range of worlds where Earth-like life might evolve. Either way, the logic we have used in this story, starting from simple physics, following its consequences into ocean and climate behavior, and then into biology and culture, gives us a method for thinking about those distant systems. You can imagine, for example, a planet orbiting slightly closer to its star, with a different rotation rate and a different sized moon. Would its tides be stronger or weaker? Would its days be longer or shorter? Would its seasons be more stable or more chaotic? How would those physical facts shape the habitats available for life? These are not questions with immediate, practical answers, but they show how deeply the moon has trained us to think about links between the cosmic and the biological. Returning home to Earth, there is one more dimension worth exploring: how our modern technologies interact with ancient lunar patterns. Artificial lighting, coastal engineering, climate change, and spaceflight all alter the context in which the moon exerts its control. Bright lights along coastlines can drown out moonlight and confuse animals that evolve to navigate by it. Sea walls and dredging can change how tides move in and out of bays and estuaries, reshaping habitats that once followed simple lunar rules. Human-driven climate change can raise sea level and alter temperature patterns, changing where tidal wetlands and coral reefs can exist, even as the tides themselves continue their ancient cycles. In some ways, Our technologies now rival the moon in their power to change local environments. The lights of a city can outshine the full moon by a huge factor. The construction of a large dam or harbor can alter water flow in a way that rivals some natural tidal channels. Yet, the moon always remains in the background, still pulling on every drop of water and every grain of sand, still setting the broad pattern into which our alterations must fit. For example, as sea level rises, high tides will reach farther inland in many places. The exact areas that flood at the highest tides will depend on how the land is shaped, where we build defenses, and how the moon and sun align. Understanding future flood risks requires combining models of lunar and solar tides with projections of human-driven sea level change. In this sense, the moon's control of life on Earth is now entangled with our own control. We have become agents that can change coastlines, climate, and ecosystems on timescales far shorter than those of orbital evolution. The challenge is to exercise that power with awareness of the larger, slower forces that continue to operate. The moon will keep turning its face toward and away from the sun, keep lifting and lowering the seas, keep stabilizing Earth's tilt, long after any particular city or culture has risen and fallen. Our task is to decide what kind of stories we want to live within that enduring framework. Do we want to be a species that ignores the rhythms that made our world habitable, building in ways that amplify damage and fragility? Or do we want to be a species that learns from those rhythms, aligning our technologies and societies with them to create resilience? There is no single correct answer written in the sky. The moon offers its steady pull and its gentle light. The rest is up to us. As you think about all of this, you might find that the moon feels different to you now than it did before. It is no longer just a backdrop for romance or a symbol in horror stories. It is a dynamic part of the Earth system, a co-author of the conditions that let you exist, and a quiet teacher of patience, cycles, and connection. You might begin to notice where it is in the sky more often, to pay attention to how bright nights feel compared to dark ones, or to think about tides when you see news about coasts and storms. You might feel a subtle thread of connection between your own daily routines and the vast, slow turning of the Earth, moon system above and beneath you. That awareness does not change the physics. The tides will rise and fall whether you feel them or not, but it can change your experience of living in this world. Instead of moving through a landscape that feels random and disconnected from the sky, you can begin to see patterns linking your body, your society, the oceans, and the orbit of a silent gray world hundreds of thousands of kilometers away. Rather than experiencing the world as something random and detached from the sky, you start to recognize patterns that connect your body, human society, the oceans, and the orbit of a quiet gray world hundreds of thousands of kilometers away. In that recognition, there is a kind of calm. You are part of a story that began long before you were born and will continue long after you are gone. The moon will still wax and wane. Tides will still flow. New generations of living things will still adapt to the patterns those cycles create. And as long as beings remain who can look up and wonder, The moon will keep inviting them to ask how and why life on Earth is as it is. That is, perhaps, the most profound way in which the moon controls life here. Not only by shaping the physical conditions in which life evolves, but by drawing minds outward, encouraging curiosity, and giving us a stable, beautiful mystery to explore until we understand it, and then to appreciate even more once we do. Now you know how the moon affects our Earth. Thank you for watching. I hope you like it and see you again in the next video.